Now that we have covered the revisions for the design of beams and slabs, let us try another example. This time we deal with the design of the staircase. The figure here shows the details of the staircase. It is connecting the ground floor to the first floor. Halfway at the intermediate level, there is a landing, and this landing is supported by the beam here. Based on the locations of the beams, this determines the effective span of the staircase. The dimensions of the staircase are given here. You can design this part of the staircase and then apply the same detailings for the following part of the staircase. Now let us look at the details. The GK given is 1.75 kN per meter square. It is stated that this does not include the self-weight of the staircase. That means later you will need to determine the self-weight of the staircase as a part of the permanent actions on top of the GKs given. The variable actions is 2 kN per meter square. The characteristic strength FCK is 25 Newton per mm square. Unit weight 25 kN per meter cube. Concrete cover 30. Steel strength 460 Newton per mm square. And the diameter of the reinforcement bar used is 16 mm. This question comprises 6 sub-questions here. We're going to solve them one by one. Without further ado, let us get started. The first questions ask us to calculate the design loops acting on the stairs flights and landing at the ultimate limit states. This part is the flights, and this part it will be the landing. You are asked to design for the ultimate limit states. The reason being here is you will need to get the moment and shear. Designing moment and shear are the ultimate limit states. Now to determine the design load, you need to first get the GK and QK. The GK and QKs are obtained already, only that you do not have the self-weight of the staircase. The self-weight of the staircase is a part of the GK. Therefore, we're going to start with determining the self-weight of the staircase. To do that, we will need the average thickness of the staircase for us to compute the weight of the staircase per unit meter. The self-weight of the staircase, it will be the average thickness multiply the unit weight. Now the question here is, how do you get the average thickness? The average thickness is indicated by the symbol T. This is the T. It represents the average thickness over the span of the flights. To get the T, you will need to get the height, which is Y, in the vertical directions, plus half height of the riser. It is as if that the steps are being filled throughout the flight, so that it gives you a constant thickness throughout the flight of the staircase. The height of the riser is given. You can take R equals to 175. Now you will need to get the Y here. Y referring to the height of this. In order for you to get the Y, you can derive it based on the principles of trigonometry. Imagine this is the going and the riser. You draw a straight line joining the going and the riser. It gives you a triangle. with an angle phi here. This forms a typical right angle triangle. And then the effective depth of the staircase slab, which is h here, the relationship with the y is represented by this right angle triangle, where the y is a vector going downward, whereas the vector of h is perpendicular to the inclined angle of the flights. It happens that the angle here is the same as the angle here. With that, we can do some interpolations comparing the two dimensions here. The relationship of the h and y here, it will be the side adjacent to the angle and the hypotenuse. The ratio between the h and the y shall be the same as the ratio of the g and the hypotenuse here. G here is adjacent to the angle. Knowing the right angles with both sides G and R here, you know the length of the hypotenuse. It will be the root of G squared plus R squared. Now you equate both ratio here. Rearrange it, you get this equation. With that, we use the equations y for us to get the distance here. The h is 175. The going G is 250. The riser is 175. Substitute them into the equations. You get the y equals to 233.6 mm. Now your next step is to determine the average thickness. It is equals to the y plus half height of the riser. The y is calculated 213.6 mm plus half height of the riser 175 divided by 2. Now you have your average thickness 301.1 mm. This represents the average thickness of the flights. Multiply with the unit weight, which is given in the questions, 25 kN per meter cube. That gives you the self-weight 7.53 kN per meter square. As for the landing, the average thickness is 175. So you use the thickness of 175 multiply with the unit weight. That gives you another self-weight. Having the self-weight of the staircase determined, your next step is to determine the GKs. The GK will be the self-weight of the staircase plus the design permanent actions. This plus this equals to this. As for the landing, this plus this equals to this. And then your QK is given as 2 kN per meter square. For the ultimate limit states, you're going to incorporate the factor of safety. The design load should be equals to 1.35 GK plus 1.5 QK. That means 1.35 times this plus 1.5 times this. You get 15.5 kN per meter square. Same goes to the landing. 1.35 times this plus 1.5 times this. Your design load is 10.4 kN per meter square. Be careful with the units. The design load now that you have calculated is on the basis of per unit square area. Now you need to convert this into an UDL. This is for you to analyze the moment and shear later. The design of the staircase is similar to the design of the slab. Both staircase and the slab are large elements in a RC structure. When the member is relatively large, very often they are wider than 1 meter width. Normally, we will design on the basis of 1 meter width. Therefore, we will convert this kilonewton per meter square load into UDL by multiplying with 1 meter width. That gives you the same magnitude of the load, except that the unit now is in the mode of the UDL. Now, whatever moments and shears that you have calculated, based on this UDL, it will be the moment and shear taken by 1 meter width of the staircase. With that, you have obtained the design loads acting on the staircase.